We're going to do 5.4 after 5.5 because that way we can create the equations to do redox titration. Everything else is the same. It's just generating the equations is a little different. So also in redox titrations, you don't really need indicators because usually when you change the oxidation state, you get a different color change. So it's fairly easy to see the end point of this titration. So the example we're going to do here is potassium permanganate, and we're going to titrate hydrogen peroxide. Here's our data here. Clearly the 25.3 is an outlier, so we're going to ignore that and just use these two, which if you average 23.9, 24.1, we're going to get 24 mils of MnO4 added to the solution. All right, so the first thing we need is the reaction. So MnO4 and H2O2. So we go to our data booklet. MnO4 is right there. H2O2 is right there. So using what we learned in 5.6, if they're on the same side, there will be no reaction. So what we have to do is look for something on this side over here, either MnO4 or H2O2, that is lower than either one of those. And as you move down, you find that we have hydrogen peroxide here. So the actual reaction is going to be this MnO4 reduced to Mn2 plus, and the hydrogen peroxide is oxidized to oxygen. So we're going to write that out here, and it's going to be MnO4 minus 8H plus 5 electrons, Mn2 plus and 4 H2O. And then the hydrogen peroxide reaction is, remember we flip it because of the oxidation one, goes to O2, 2H plus 2 electrons, and you want the electrons on the opposite sides. Now clearly the electrons don't cancel, so we have to multiply this one by 5 and this one by 2, and then we add them together. And when you do that, you get 2 MnO4 plus 6 protons plus 5 peroxide molecules goes to 2 plus 8 waters and 5 oxygens. That's the overall reaction. Okay. And you can see it matches up because we said it was acidified hydrogen peroxide, and we know it's acidified because we have the H plus here. All right, now it's a standard titration. So here's the 3 trials we did. We just said that we ignored the first one there, averaged the next 2, so an average of 24 mils of MnO4. So the moles of MnO4 minus are going to be the mils, so 0.0240 liters, 24 mils, times its concentration, which is 0.025, which gives us 6.00 times 10 to the minus 4 moles of MnO4 minus. Then we use the mole bridge, which was the whole reason for doing the equation. And we go, okay, 6.00 times 10 to the minus 4 moles of MnO4 minus. 2 moles of MnO4 is 5 moles of peroxide. So 5 moles of H2O2 is 2 moles of MnO4 minus. So moles of those cancel. That gives us 1.50 times 10 to the minus 3 moles of hydrogen peroxide. I want to know the grams of it because we're figuring out the percent concentration. So I'm going to multiply that by its molar mass, which is 34 grams H2O2 for every mole, which gives us 0.0510 grams of hydrogen peroxide was in a 5 ml sample. So what's the percent concentration? Well, the percent concentration is going to be the measured, actual, whatever you want to call it, actual amount divided by theoretical. So the actual, what we measured, is 0.0510 grams. Theoretical is going to be, well, we're assuming every mil has 1 gram, and we did 5 mils. So that's going to be 5.0 grams multiplied by 100%, and you're going to get 1.02% H2O2. Okay. That's it. Everything else is the same. The only real difference is calculating this first equation, which is what we use the activity series to do, and then balancing it out so the electrons disappear, and then it's a regular titration question. Use the mole bridge, figure out the mass, answer whatever they're asking you to find. All right, finish exercises 5-4, and I'll see you soon. All right, bye-bye.